Hi, good morning. This is the e-learning video for Honors Math 3. We are moving on to section 14.3. This is going to be part 1. So we are looking at now one-sided limits and also limits for continuous functions. So we're first going to look at example number 1, which is a piecewise function. Alright, so here what I have, here's our piecewise function. This one has 3 pieces. And I went ahead and graph these functions. So again, we can look at it in terms of the graph as well. So here is the graph for the part of the function where the domain is less than 3. Alright, so again, 2x is going to be a line. Alright, but since it only goes up to 3 and not including 3, we're going to have like kind of this hole or this place where the function is undefined. So that's that graph. Here we have the functions equal to 0 when x is equal to 3. So that's what this point is right here. Alright, and then finally the third part of this piecewise function is this linear part, negative x plus 4. So again, we're going to find that function for all x values greater than 3. So again, I plug 3 in for x, I get 1, but it's undefined there, so we have this hole. Alright, but then we find other points for this function. If I plug 4 in, I get 0, so there's that point. That establishes this part of our graph, our piecewise. Okay, so now we're going to go ahead and find these, what's called one-sided limits. Alright, so we're going to find the limit of this function as x approaches 3. So now you're going to see this new notation. Right, so again, this is not a negative sign. This is a symbol that represents we're going to approach 3 from the left side. Okay, so here's 3 for our domain. So we're going to be coming in from the left. So coming in from the left means we're going to be approaching using this part of the piecewise. Alright, so as x approaches 3 from the left, we are coming to this value, which is 6. So the limit of this piecewise function is 6. And where this is headed, when we get to 3, right, is going to be 6. An output of 6. Here we're finding the limit of this function as x approaches 3. And this plus sign means from the right. Okay, so here's 3. So that means we're coming in from this direction, from the right. So that means we're using this part of the piecewise, coming in from the right, and we're approaching this value, which is 1. Okay. Then we get to this, find the limit of the function as x approaches 3. Now we don't see a plus or a minus here, so it's not left or right, so it means we're coming in from both sides. So coming in from the left, we know it goes to 6. Coming in from the right, we know it goes to 1. Alright, but as we talked about before, because, right, it does not come to a common place from both the left and the right, the limit does not exist. Okay, because the output from the left and the output from the right for that function, for that limit, is not the same. The limit does not exist. Okay? Alright, so I'm going to go ahead and graph the second piecewise. Alright, so now we're going to go ahead and graph the example number 2. So here we have negative x squared. Alright, so for all values of x that are less than or equal to 0. Alright, so we're going to go ahead and plug that in. Alright, so then x squared means it's a quadratic, so it's going to be a parabola. Alright, so I plug 0 in for x, negative 1 in for x, negative 2 in for x. So I'm going to get this part of the graph. There's my upside down parabola for all x values less than or equal to 0. Here we're going to have absolute value of x, which we know is a V shape. But we're only looking at part of the V where x values are greater than 0. So that's going to be this straight line graph coming up like this. Okay, so there's the graph for this piecewise function. It's two pieces that appear to be connected. Alright, so now let's go ahead and evaluate the limit of this function as x approaches 0 from the left. So again, we're coming in from this direction. So we're going to follow this part of the graph. So coming in from the left, we're approaching 0. So as we approach 0 on the x-axis, we are approaching 0 on the y. Alright, so the limit of this function as x approaches 0 from the left has an output of 0. Find the limit of this function as x approaches 0 from the right. Again, this 0 means we're coming in from 0 on the x-axis, coming in from this direction, from the right. So it means for our graph, we're coming in this way. So as we approach 0 on the x, we are coming closer and closer to 0 on the y. So the limit of this function as x approaches 0 from the right side is also equal to 0. Okay. So finding the limit of f of x, finding the limit of the function as x approaches 0, again, we don't see that plus or minus, so that means we are approaching it from both sides. And as we can tell, right, since we're approaching 0 from the left, we get an output of 0. Approaching 0 from the right, we get an output of 0. Because they both go to the same place, the function at the limit of the function as x approaches 0 is 0. Alright, so here's the theorem. If the limit as x approaches c from the left is equal to L, limit as x approaches c from the right is equal to R, then the limit as x approaches c exists only if L equals R. So here, from the previous two examples, again, because, right, from the left side and from the right side, these two values are not equal, the limit for this particular function, as x approaches 3, does not exist. But for example number 2, because, right, the limit from the left and the limit from the right are exactly the same, then the limit for this function does exist, and it is that particular value. Alright, so let's go ahead and move on to example number 3. Alright, so here's the graph for example number 3. So here's our piecewise function. So we have an exponential expression, we have a constant value, and then we have a cosine wave. Alright, so for the three parts of the function, so e to the x as x is greater than 0 is going to be this curve. Again, it's an exponential. And function at x equals 0 is defined at its output is -1. So that's this point right here. And for this cosine wave, as x is less than 0, so it's going to be this part right in here. Okay. Alright, so find the limit of this function as x approaches 0 from the left. So again, here's 0 on the x-axis, so we're coming in from the left. So we're using this cosine wave coming in from the left. So we're coming closer and closer to an output value of 1. Find the limit of this function as x approaches 0 from the right. So coming in from this side of 0. So that means we're using this function, this graph right here. And it's also approaching 1 on the y-axis. Right. And based off of the theorem that we stated here above, because the limit coming in from the left and the limit coming in from the right of 0 matches, then the limit of this function x approaches 0 is going to be that value of 1. Okay. Alright, so now we're going to define what it means for the function to be continuous. So here are the three requirements for a function to be continuous. Alright, f is defined at x equals c, meaning that when we plug in our c value into our function, we do get an answer. Right. The second requirement is the limit as x approaches the c value from the left is equal to the output of f of c. The limit as x approaches c from the right is equal to the output, when you plug c in for x into your function. Alright, so if all three of these requirements are met, then the function is deemed continuous. Alright, if the limit as x approaches c for that function is that specific output. Okay, so let's go back to the previous three examples and figure out which one of these three examples are continuous. Okay, so now, not about limits, it's about, right, are these functions continuous? So we take a look at example number 1. Okay, so then the first requirement for continuous is that the function is defined at c. Alright, so the c value is 3. So I plug 3 in for x. Do I get an output? I do. Right, again, here's when x is 3, there is a defined output. So number 1 is satisfied for the requirement for continuous. Number 2 requirement is the limit as x approaches c from the left is that output. Alright, coming in from the left. Okay, we see that when we plug in coming from the left, it is 6. Coming in from the right, it's 1. So because it does not equal that output of 3, right, number 1, this function is not continuous. Alright, example number 2. Okay, so again, we're asking the question, is it continuous or not? So the first requirement for continuous is that the function is defined at c. So when we plug in, we look at our graph, and we see that at 0, the function is defined. Okay, so we satisfy requirement number 1. Requirement number 2 says coming in from the left, does that output of that function equal output at f of c? And it does. Right. And coming in from the right, does that output equal that output of at c? Yes, it does. So, alright, this one, it is continuous. All the requirements are met. Example number 3. Is the function defined at c? Yes, I have the defined output at c. As x approaches c from the left, does it equal that same output? No. Okay, so once we say no, we know for a fact that now this is not continuous. Alright, so we're going to continue this video lesson with video number 2. So please go on to video number 2 for this lesson.